Hello and welcome to this talk on non-imaging external counting methods for patient monitoring and whole body dosimetry. My name is Jan Taprogge and I'm a medical physics expert at the Royal Marsden Hospital.
First of all, I have to say that I have nothing to disclose in relation to this presentation. So first of all, I wanted to start off with talking about why we should be doing whole body dosimetry or where it can aid in molecular radiotherapy. And so one of the main organs at risk when performing molecular radiotherapy treatments is obviously the bone marrow. And if we're talking about bone marrow dosimetry, performing image-based dosimetry often is very prone to lots of inaccuracies, and it's very often very resource intensive. So you have to take multiple images of the patient, depending on where we want to outline the bone marrow on the images and everything. It's very complicated. And whole body dosimetry really is like an easy way around this that has been used quite a lot in the past and is still being used in certain therapies because it doesn't involve any imaging. It can be done with certain types of radiation detectors, and I'm going to be talking about that later throughout the talk. Obviously, we have to make certain assumptions. We obviously have to assume that the whole body absorbed dose is linear with the bone marrow absorbed dose, and something that also we're going to talk about at the end of the presentation is that we can use those measurements to individualize patient radiation protection restrictions as well. So just a couple of examples of where in the past whole body dosimetry has been used, and I think it all started off a little bit with radioimmunotherapy with this I-131 tocilizumab. And in the phase 1 activity escalation study, they already used whole body dose, and they treated to a maximum tolerated absorbed dose of 0.75 gray. And what they found was that to achieve that 0.75 gray across different patients, there was a very wide range of activities they had to give, ranging from about 2.1 to 5.7 gigabecquerels. So really showing that if we want to treat patients equally, it was really important that we use the whole body dosimetry to standardize those treatments. The second bit where whole body dosimetry really has been used extensively is I-131 MIBG for neuroblastomas. Here, it's often the aim to give 4 gray across 2 therapies with an initial weight-based administration, followed by a second dosimetry-based administration. And then that is then done supported with peripheral blood stem cells or bone marrow support, because we're obviously giving quite a bit of dose to the bone marrow. And so these are some of the data that comes from our center where we routinely perform those I-131 MIBG treatments for neuroblastomas, and we're just showing kind of the large interpatient variability of the whole body absorbed doses that we're delivering with a fixed activity weight-based administration. So this is data from the first administration of patients, and the second administration will be adjusted based on kind of the whole body doses that they've received. Showing that there's for most patients, I mean, we're even with a weight-based administration, we do more or less end up with this roughly 2 gray that we're aiming to deliver. But there's some patients where we're really under or over treating. For example, patient 2, where we gave about 1.4 gray. So we really have to top up the second administration more to achieve those 4 gray overall. And then patient 3, where we actually, even with the first administration, already gave much more than the 4 gray intended dose. So it's good. Something then we can flag this to the clinicians so that they're aware of this. And second of all, in this instance, for example, the patient obviously wouldn't have received a second administration. There are really a lot of guidelines out there that help you with the setup of whole body dosimetry, and I've put them here all on the slides, kind of from the E&M dosimetry committee. There's guidelines for bone marrow and whole body dosimetry. There's guidelines for pre-therapeutic dosimetry of blood and bone marrow dosimetry in differentiated thyroid cancer. IPEM, UK body has published quite a lot of on dosimetry for radionuclide therapy in one of their reports. IDAC, which is the internal dosimetry user group in the UK, has also got a whole body dosimetry guidance sheet, and the E&M obviously has as well dosimetry guidelines on I-131 MIBG dosimetry. So just going through the whole process, And obviously the first bit we have to talk about is really the radionuclide calibrators, because they really form the first step in our whole process, and they need to be properly calibrated. They need to be a robust quality assurance program, because we will use those calibrators to, first of all, calibrate other equipment that we're using as part of our whole body dosimetry calculations or any other dosimetry calculations. And they obviously form part of the measurement of the activity that would have actually given to the patient. So it's really important that they're properly set up, and they should be traceable to a primary standard for each radionuclide that is being used. So then obviously, so we need to measure the activity that is retained in our patients at several time points to kind of like measure what we call the time integrated activity. So we need to know how much activity is left in our patients at each time point. And for that, we either can use serial whole body imaging, or like I said, we want to obviously ideally don't want to take too many images of our patients, not use too much of our camera time. We can use radiation detectors for that. I've put on just a couple of kind of like the guidelines on like the QC programs, but it's really important that we obviously understand our radiation detectors before we use them, including things like linearity and their time characteristics. So in the way of the probe setup, there are different approaches that have been used, and so either you can either use a ceiling mounted detectors or any kind of like fixed geometry setup. So in our case, that's an example from our center, where we've got our ceiling mounted detectors in the above the patient bed. So we do our measurement with the patient lying on the bed, and so you always have the same kind of geometry. The problem is that you obviously need some kind of shielding, kind of like to collimate your detector, which requires additional support in the ceiling often. But it is great because, like in our case, like the detectors are hooked up to a computer outside the patient room, so you're really minimizing radiation exposure to staff. The second option, which is obviously often more available in most nuclear medicine departments, is to use any kind of handheld radiation monitors. And really important here is that they're always used in the fixed geometry, or the fixed distance from the patient, which is normally about 1 meter from the patient. You just need to make sure that you reproduce that setup every time you remeasure your patient. And then, so we're doing our measurements with our radiation detectors. So we obviously then have to like quantify how much that count rate that we're measuring corresponds to how much activity that corresponds in our patient. For that, normally what is done is we're kind of like doing a first or baseline measurement, where we know exactly how much is left in the patient. So they're being done right after the patient has been administered and before the patient can go to the toilet or anything, because then we know exactly how much activity is in the patient, and we can directly convert our count rate that we're measuring in our radiation detectors to a certain activity that was given to the patient. We do anterior and posterior acquisitions at each time point, just to, as much as possible, account for any kind of like scatter or any kind of like attenuation in our patient. And obviously we have to assume that kind of like the redistribution within the patient really has very little effect on the measurement itself. And like I said, I think the main point here really is like you need to reproduce your measurement setup every time you redo the measurements for a certain patient. So in our case, that means we have our patient on a bed underneath our radiation detectors, and we always make sure that the bed is at the same height, and the same number of pillows are being used and all of those kind of things, just to make the measurement geometry as identical as possible. So yeah, this is kind of like the setup, and like I said, in our department, so we've kind of like a concealed ceiling mounted Geiger counter just above the patient bed. So the patient always lies in a reproducible position, and then the whole setup is connected to a computer outside the room, where we can then take serial measurements over time to see how the activity retention in the patient changes. So we get from our radiation detectors, we get our count rate or dose rate, or whatever the output is. So the first bit we obviously have to do is to correct for the physical decay. We have to correct for background. So normally what we would do is take a background reading with the patient in place, just before the therapy. So we've got like a baseline measurement or background measurement that we can then subtract from any subsequent readings. And if you have assessed the dead time of your detector, which you should do, then you obviously you know if you have to correct for dead time of your detectors depending on like what count rates you're measuring in your patients. Then, like I said, so we take anterior and posterior measurements for all of our patients. And so the activity retained at each time point is then just calculated as the activity at time point 0 times the geometric mean of the anterior and posterior count rates at time point t divided by the anterior and posterior count rates at time point 0. And then you're straight away getting your activity retained at time point t. So we obviously need multiple of those measurements, and you would should take them as often as possible, obviously taking into account of not to inconvenience the patient too much. But if you take the more measurement you take, the more likely you're able to spot any kind of like erroneous measurements, and it really increases your confidence in the fit that you later will achieve. And if you're using multiple exponential phases, then you really should have a minimum of 3 time points per exponential phase that you're fitting. To kind of like set up your measurement schedule is really good to like use any kind of like literature that you have got on that radiopharmaceutical and then on their excretion and uptake patterns in patients. So for thyroid cancer patients, for example, we do roughly a reading every 3 to 4 hours while the patient is awake, so we wouldn't wake them at night until the patient is discharged and then leaving the hospital. Sometimes, if we see that there's a very slow retention phase, you should be taking additional measurements once the patient has left the hospital, just to make sure that you're accurately capturing that slow phase at the end and get an accurate estimate of your whole body dose. And then once you've got all your data, so this is an example of one of our MRBG patients where you can see kind of like we have got multiple measurements each day the patient is in. And then you can either use linear or exponential interpolation if you've got quite a lot of data points, or you just use multi-exponential fit and you select the appropriate function, so how many exponentials based on kind of like statistical tests or any kind of like known physiological processes of pharmacokinetic behavior that you know about. And then obviously it's obviously always important to kind of like look at the uncertainties as well. And the ENM obviously has published a great uncertainty paper where they kind of like talk about all of those kind of things. Then now we've got our kind of like a total number of radioactive decays in the whole body. We obviously need to combine that with an S factor to get our radiation dose. Here you should obviously be using age-appropriate models for the S factor scaled according to the patient mass. An example here is the ENM from the ENM guidance for I131 MRBG dosimetry. So this is the S factor that they propose in their guidance for I131 MRBG. And like you see, it has the patient mass built in there. So you scale for the patient using the patient weight. You scale the S factor for your whole body dosimetry calculations. So coming back to the example that I just showed, so like I said, it's an MRBG patient treatment. Like I said earlier, the treatment schedule here is 2 + 2 gray. These are the measurements from our initial first therapy that was given on a weight-based approach. And then we will use that to calculate the required activity for the second treatment. So for this patient, like I said, so to get to the whole body dose, we need the time integrated activity for this patient is roughly 200,000 megabec hours. And we need our S factor. We use the S factor that I showed a couple of slides before, scaled to the patient weight. And then we end up with roughly 1.4 gray delivered in the first therapy. So to achieve an average of 2 gray or a total of 4 gray across the 2 treatments, we need to deliver at least 2.6 gray in the second therapy. We obviously know how much activity we've given in the first therapy, so we can just calculate our gray per gigabecquerel factor and can just predict with that the activity needed for the second treatment. And then we should obviously do whole body dosimetry after the second treatment to confirm that we've given overall the desired 4 gray in the 2 therapies. And then so just to kind of like finish off a little bit, I want to talk as well about radiation protection. So when you're doing those whole body measurements or dose rate measurements on a patient, they really can be used to personalize like the restrictions or like the radiation protective advice that you're giving to patients when they're leaving the hospital. Because often this is kind of like done on generic advice based on previous patients where we've got dose rates for certain therapies, and we've got like assumed contact patterns. But ideally, if you do those whole body measurements and you know how much or how the excretion pattern looks for a certain patient, you really can use that kind of like to personalize the advice that you provide to a patient when they go home, how they have to stay away from certain members of the public, how long they have to like keep their distance from their household members, including kids or something like that that might be at home. So it's really a great thing that we can use here. And so for that, we obviously like you always have to assume some kind of contact models, because and this can be generic contact models, or you can talk to the patients about how much time they spend with certain people in the household, with members of the public, such as colleagues or something like that. And so you end up with a kind of like a normal contact pattern at certain distances. And then you can apply kind of like contact restrictions. You can say, for example, okay, avoid prolonged contact, which we say is more than half an hour, close to, which is less than a meter, contact with any kind of patients while you're in your restricted contact phase. And so then you end up with kind of like your restricted contact pattern. And this restricted contact pattern, together with your isolation period, you can really use then to kind of like achieve the dose constraints that are set in your legislation, so that you're working towards to ensure that members of the public or members of the household are not exposed too much from our therapy patients going home. So like you say, so like we have our kind of like patient dose rate measurements and how they change over time. And so we have got our first isolation bit. Normally, for a lot of therapies, patient stays in for a certain amount after the therapy, so there's no contact with any members of the public or members of the household. But then they go into kind of like a restricted contact pattern where we give them advice on how long to stay away from certain members of the public or members of the household. So during that time, still, even if there's contact restrictions, they will still give a radiation dose to those to those members of the public or members of the household. And then at some point the restrictions end and they go into kind of like a normal contact pattern again, and where then the dose really accumulates more depending on how much is left in the patient. So like you can see here, so this example, kind of like we have a little bit of dose accumulated during the restricted contact, and then really once the normal contact resumes, we're going up. And in this case, you would actually exceed the dose constraint that we have set ourselves. So what can we do? We kind of like increase our restricted contact pattern, or we could keep the patient in for longer in isolation, depending on what is possible. But so in this case, I've just looked at kind of like extending the restricted contact patterns, and then you see that overall kind of like the dose that we provide to our members of the public or members of the household goes down. So we can really use that to guide us. So yeah, so hopefully I've given you a bit of an overview of where whole body dosimetry is useful, and where it can be used and where it has been used in the past, and how kind of like to set up your whole body dosimetry service. Like I said, there's lots of guidelines out there. Really have a look at them and read them, and it really shows you what kind of setups to use, at what time points to measure, and all those kind of things. Like I said, compared to image-based dosimetry, whole body dosimetry is really easy to implement, less resource intensive. So it's really a great start to start off with dosimetry, especially because the bone marrow is often the organ at risk that we're interested in. And if we're assuming that the whole body absorbed dose scales linearly with the bone marrow absorbed dose, it's really a great tool kind of like to avoid any toxicities in our patient. And then just to finish off, I obviously showed you a little bit how you then can, on top of that, use those whole body retention measurements to personalize the radiation protection restrictions that you're giving to patients, and so that like the dose to any members of the public or members of the household are limited as well. So thank you very much for listening, and I hope you enjoyed these slides.